Welcome to EDU World Space.
Here we're going to find the electric field at various positions along the x-axis, produced by two spheres, both of which have the same radius, big R, and are uniform in charge. So there are a couple things that we need, but they basically come from Gauss's law. And the first idea is that as long as you're outside a sphere, a charged sphere, especially a uniform charged sphere, acts like a point charge at its center, has the electric field equal to point charge of same Q. Okay, so we're going to need the point charge electric field, and that is Q, absolute value, over 4 pi epsilon naught r squared. Okay. If you are not outside the sphere, you will have to do an integral in accordance with Gauss's law. You may have to find the enclosed charge, which is equal to, for a uniform sphere, the density times the volume enclosing. Okay, so let's take a look at some examples. The positive sphere is on the right, and the negative sphere is on the left. If you start at x equals 0 and you show the electric fields due to these two arrangements, there is no electric field in the middle for the positive charge. It is all due to the negative charge, and it points towards the negative charge, just straight towards the center of the negative charge, and it has a value equal to, it's in the positive x direction. You are 2r away. Let me show the distance here. Oh, so you are 2r away from the middle of that sphere. And so that minus electric field is Q over 4 pi epsilon naught times 2r squared. And that's a positive. So notice that the positive or negative parts of the electric field come from the way it points, not the charge that's in the electric field. And that is why it is always good for both force and electric field to do the absolute value when doing a calculation. You are finding a magnitude. The direction comes from attraction versus repulsion. Okay, let's go to the next one. At x equals r over 2, you are sitting in the middle of the positive sphere, and you are r over 2 away from the center of the positive sphere, and your 3/2 are away from the center of the other sphere. So you have two distances. Let's take a look at the electric field. It is basically pointing out from the positive sphere. So we'll say E plus. And it is pointing in to the negative sphere. So you're simply going to add those two together to get your E total. That is, add the two magnitudes, E plus plus E minus. Now, the E plus is interesting because we have to think about the enclosed charge in a volume centered at r over 2. So this is where we're going to have to use the density. E plus is equal to 1 over 4 pi epsilon naught. And the amount of charge is going to be equal to Q. And we want to do it sort of proportional wise. R over 2 cubed compared to R cubed. And so we see that that is Q over 8. Over 4 pi epsilon naught. And I forgot my R squared, which is, at this point, R over 2. Yeah. So hardest thing is keeping track of all these distances and densities. This is probably the hardest little regime. Whoops, I already have the pi. And so that's R epsilon naught R squared over 4. Yeah. And yeah, there's a factor of 1/2 in there. And the E minus is kind of cumbersome too. We don't have to integrate. We're outside of the negative charge distribution, but we do have to put in 3/2 R squared, sorry. And that is, after all is said and done, Q over pi 9 pi epsilon naught R squared. And so adding those two together, yeah, you have to find a common denominator, which is 9 times 8, or 72. And let me just summarize that result. We're not at x equals r yet. So E total is going to be Q over 72, sorry. And then 9 plus 8 is 17. And it is positive because it points to the right. Okay, now that took a lot of space. Hopefully, let's move some things down so we have a little bit more room without getting these things confused. So our next is x equals r. And we are right then in between the two spheres, and we are equidistant from both of them. But let's again draw the electric field due to both of them. Not surprisingly, it is going to be positive away from the plus sphere, and the negative sphere is also going to point to the right. They should be equal because we're equal distance from the centers. So this one's going to be an easy one. We need an easy one after that last one. And that's just twice one of them. It doesn't matter. And there, since we're outside both spheres, we can simply just add them up. Okay, whew, that one was good and easy. All right, and then last one's not too bad either. We are outside both spheres again. x equals 3r. So we are right on the edge of the negative sphere. And let's draw the electric field. So the positive sphere always goes to the right. But now at that point, the negative sphere is going to be pulling to the left. And let's see, we're a distance of 3r, of course, from the positive sphere, and a distance of r from the negative. Again, we'll use superposition, but this time we are going to have to subtract the E negative, its magnitude. So notice that the direction comes not from the charge necessarily, but the direction that the electric field points. And we're outside both spheres, so we don't have any funny density business. Okay, and let's see, that comes out to be all said and done. We've got a 1/9 minus 1. Okay, and that's minus 8/9. So all said and done, we can simplify our electric field down. That's always good to put in some fractions. Simplify a fraction down. All right.